Welcome to the next section of the course. So, here in this section, we will be focused on forming. So, rolling is a deformation process in which the thickness of the workpiece is reduced by compressive forces exerted by the two opposite rollers. So, one is rolling in this direction, the other one will be rolling in this direction. If both rolls in the same direction, the input will not happen. It is something like a sugarcane juice making. You have two rollers. The sugarcane is fed inside, and when it is fed inside, you see the thickness reduces and the juice comes out. So, next time what we do is we take it out and then we refeed it. Or what you can do is you can try to reverse the rollers, whatever thickness reduction is there, you can pull it back, then try to reduce the thickness T, the thickness or the gap between the rolls, you reduce it. So, then what happens? The next squeezing happens. Like this, you do multiple times to get the best out of it in a sugarcane. The same thing can also be done multiple times, so that in each operation, you try to reduce it at a certain delta x. So, you can't get from 1 millimeter to 0.1 millimeter in one shot, because then it undergoes a strain hardening rate, and then you will have material feeding also will not happen properly. So, what we do is we do step by step by step. First time we roll from 1 millimeter to 0.8 millimeter, then from 0.8 to 0.6 millimeter, then 0.6 to 0.5 millimeter, then to 0.4, then to 0.4, then we go up to 0.3, then we go up to 0.2, then we go up to 0.15, then we go up to 0.12, then finally we go up to 0.1. So, all these things are in millimeter. We go multiple steps, right. So, multiple steps means each time the metal is out, we try to reduce the thickness, then feed it inside. So, you can do like that, or what you can do, you can have series of rollers which are placed one after the other along the length direction, and the reduction can be done. That is also possible. If you want to have continuous process, then we put all the rollers in serial and it drags it into it. So, if you have only two rollers, then you have to do one after the other after the other. Most rolling is carried out by hot rolling, called as hot working, by hot working called as hot rolling, owing to the large amount of deformation required. If the deformation is very large and the forces are not sufficient, then we always go heat the workpiece. So, this is the original grain which is there when you try to push it inside. So, the feeding direction is this. The roller are moving in opposite direction, so that it bites and drags the material outside. So, here if you see the original grains, the grains are getting elongated, and then you try to have the new grains getting formed when it comes out of the roller zone. So, this is the deformation zone. When it comes out, you get a elongated grains. These are elongated grains, and the new crystal is also getting formed. Rolling, the material pulls by rotating rollers and simultaneously squeezes the work between them. So, pulling, so here it has two things, one is pulling, another one is squeezing. Okay. Hot rolled metal is generally free of residual stress and property of isotropic. The disadvantage of hot rolling we have already seen. You cannot get very close tolerance, and there can be a possibility of oxides getting formed. So, why is it so much we are talking about it? Because these oxides which are getting formed are brittle in nature. So, they will try to form, and these oxides will be formed on the top. The oxides are brittle in nature. In the next time when you try to roll this, it will try to easily crack, and this can scratch the roller as well as the workpiece. So, oxidation scales should be avoided. So, which becomes very common when we start working on hot rolling. For steels, desired temperature for rolling is around about 1200 degrees Celsius. The heating operation is called as soaking. We saw this in the previous chapter when we started looking into heat treatment, soaking, and the furnace in which it is carried out is called as a soaking pit. Blooms, slabs and billets are different types of workpieces which are there. A bloom is nothing but a square cross section area of 150 millimeter cross 150 millimeter or larger. Slabs are rectangular cross section with a width of 250 millimeter or more, and the thickness is 40 millimeter reduced. Earlier was 150 bloom, slab was 40 thickness wise I am saying, and the width is expanded. Now, when we talk about billet, it is a square of 40 mm on the sides or larger. So, the bloom is large, billet is small, slab is much small. Right? So, that is what we are trying to say. So, this is a bloom, this is a slab, and this is a billet. From this, by a rolling operation, you can try to produce I channels. We can try to produce railway tracks. So, how do you do that? So, if you try to do the cross section area, this is the roller. When you look from the side, this is how the roller looks like. So, here when we look from the front, what will happen is you will see they will have something like this, the roller. So, this will try to bring this structure. So, it can be something like the roller cross section is changed, so that you try to get the required output. Right? In slab, it is straightforward. So, rails are made from bloom by a rolling process. Then slabs, you can make coils, plain sheets, all these things out of it. Billets are bars and rods can be made for operation. Further flattening of hot rolled plates and sheets is often done by cold rolling process. Major change in shape is done by hot, and then further you can do it in cold. So, cold rolling strengthens the metal and permits the thicker, tighter tolerance on the thickness. So, hot rolling did not happen now, it has a history. The rolling of the rolling of gold and silver by manual methods dated from the 14th century. Leonardo da Vinci designed one of the first rolling mills in 1480, but it is doubtful that his design was ever built. In around about 1600, the cold rolling of lead and tin was accomplished by manual operation of rolling mill. In 1700, hot rolling of iron was being done in Belgium, England, France, Germany and Sweden. In Europe, it typically happened. These mills are used to roll iron bars into sheets. In the modern rolling practice dated 1783, when a patent was issued in England for using a grooved roller for producing iron rods or iron bars. The Industrial Revolution created a tremendous demand for iron and steel simultaneously for the development of rolling process. The first mill for rolling railway rails was started in 1820 in England. The first I-beam was rolled in 1849 in France. So, you see casting had a very long history. It started from BC and then it came to AD, but rolling started, there are evidences only in the AD. So, this was the initial roller which was there, and this is the little advancement we have. So, you had a flywheel. This flywheel is rotated to give a huge impact. So, that is done. So, then rollers were also done. Even today, when we want to do sheet bending operation, we have these two arms which can reduce or increase the spacing here, and then we try to apply load manually and then get the output done. When we talk about flat rolling, it involves the rolling of slab and sheet. So, this is a roll, okay, this is a roll, this is the input material height, this is the width. V naught is the velocity with which it is pushed inside, Vf is the velocity with which it comes outside, H naught is transformed into Hf, V naught is transformed into Wf. So, moment there is a reduction in the thickness, there will be an expansion in the width. Okay. So, V input V naught and Vf will not be the same. Okay. So, when we try to look at further details, this is the roll we have, which has a radius of r. The velocity with which the roll rotates is called as Vr, right? And there is an angle which we have marked here. This is called as the bite angle. Okay, bite which chews and pulls it inside, bite angle. So, you can see here there is an entry zone, there is an exit zone, right. So, here you can see here there are tensile there are compressive loads which are getting applied at this point. The distance from the entry to the exit zone is called as the rolling gap L, right. And from the start to the end, from the entry zone to the exit zone, in between you have a point which is called as no slip point. We have a point which is called as no slip point. This is very important. So, entry zone, exit zone, no slip point, and then you will have a gap, rolling gap of L which is there. So, now when the roller has to be rotated, there has to be torque which is given to the roller, which is attached to a motor. So, this gives the torque F. So, this is the length L which we have said gap, the roll gap L, and you can see here this is the alpha. This is the alpha. So, this is the neutral point. So, you can see F compressive acting here, and entering inside you will have a small tensile which rejects here. So, at this point you will have a no slip point. So, in rolling we can make slabs, sheets, strips and plates. So, little bit of analysis if we do. So, in flat rolling the work is squeezed between two rollers, so that the thickness is reduced and the amount of reduction is called as the draft. Draft D is nothing but T original minus T final. So, T naught is the starting thickness, T f is the final thickness. The draft is maybe expressed as a fraction of the starting stock thickness. So, it can be in terms of a reduction. R is nothing but D by T naught. You can have it as a reduction R. The increase in width of the roller by spreading is called as W. We have seen everything here. Theta, the rolling radius is R, the bite at this point is called as neutral point, and here the roller pressure with which it is entering inside is called this P, and then you have a contact length L. The velocity of the rolls is VL, the velocity with which the component goes inside is V naught and T naught, TF, VF. So, in rolling the conservation of matter is preserved. So, that means to say the input equal to output. So, volume consistency happens. So, the volume of the metal exiting the roller equals the volume entering in. T naught, W naught, L naught will be equal to TF, WF, LF. The length will increase, width will increase, the thickness will reduce. Okay. Also, in rolling process, before and after the volume rate of material flow must be the same. So, V naught equal to Vf. So, T naught, W naught into V naught equal to Tf, Wf into Vf. So, theta is arc angle made by the roller with workpiece. R is the radius of the roller, Vr is the surface velocity, V naught will be lesser than Vr, which will be lesser than Vf. At the no slip point is known as the neutral point, the velocity of the work and the roller is equal on either side of this point. The slipping and friction occurs between the roller and the workpiece. See, the amount of slip between the roller and the workpiece can be evaluated by the forward slip. S is equal to Vf is the output, Vr is the roller velocity, Vf is the output velocity divided by Vf. The true strain expressed by the work rolling is strain is equal to a natural log of T naught by Tf. So, when we talk about the rolling analysis, the friction force in rolling on the entrance side is always greater, on the entrance side is greater, so that the net force pulls the work through the roller. So, friction force at the entrance side is greater, important point, right. So, that what happens, it can be pulled. There is a limit to the maximum of reduction you can have. D max is the maximum draft reduction in one shot is equal to mu square into R, where mu square is the coefficient of friction, R is the roller radius. So, the equation indicates that the friction, if the friction were 0, the draft would be 0. If it would be impossible to accomplish the rolling operation. So, if the friction force is 0, I put lubricant, bring it to 0, then D max, it will just slip and nothing will happen. So, the rolling peak pressure is always at the neutral point. This is also very important. No slip point, the peak pressure, the rolling pressure will be very high. This is the L. What is L? Start to L. This is the rolling, gap, whatever we saw that. This is gap L. So, what are the outcomes? If for a given coefficient of friction and rolling pressure, MPa sufficient to perform rolling, force F is required to maintain the separation between the two rollers. So, F is nothing but W times P, the pressure applied for a small L delta L length. L is the constant between the roller and the work. Y average is the average flow rate. W is the width of the thing. So, the rolling force can be calculated as average flow stress, which you have seen the formula earlier, width into L. So, here the contact L can be figured out root of R T naught minus Tf. So, the torque will always be 0.5 times F into L. It is a simple calculation. You can try to find out what will be the torque force required for a roller to be given such that it can try to deform. So, the power required, so we know the torque, from there we calculate the power. So, the power required to drive each roller is a product of torque and the angular velocity 2 pi n. So, the power will be equal of each roller is 2 pi nt, as the roller mill has two powered ones. So, the power is equal to 2 pi nt FL. So, n is the rolling speed. With this, what we can do is we can try to figure out what power you should apply for a rolling operation to try to deform from this thickness to this thickness. As I told you earlier, the reduction cannot happen in one shot. So, what we do is we try to have these rollers multiples. So, when these rollers are kept one or the place where they are kept or the machine is called as a rolling mill. Various rolling mill configurations are showed for various applications. So, what we do is, in order to see the friction, the draft is equal to mu into R naught. So, there is a limitation reduction of this thing R naught, right? This is the roller radius. So, that is why we also try to reduce the roller radius, so that you get a draft reduction. So, the rollers mills, the rolling mills can be 2 mill, 3 mill, flow 4 mill or cluster of mills, or tandem. This is called as tandem mills. Increasing the rolling mill increases the total force read on the forming sheet. Owing to the high rolling force, these small rollers would deflect. So, we have supporting rollers on the back. That is what these rollers are called as supporting rollers. Same way here, supporting, these are supporting rollers. The rolling, we can also make threads. So, in the die, if you have this threads made, so a screw is kept there, it is just rolled. So, rolling need not be always cylindrical, you can also make flat. If the geometry is given, you roll it one shot, you get the output. So, you get a finished one. So, it is used to form threads or on cylindrical shafts by rolling between the two dies. It is also used for mass production of external threads. This is thread rolling. So, modification of the roller, you can try to get the output. There is a variation which is called as ring rolling. If I have to produce rings of a large diameter, we start with a smaller one and we keep expanding. So, here what we do is we have two edging rollers, then we have one ideal roller, one roller which is attached. So, this is attached to the feed. So, here what happens, these two rollers, the edging roller will try to squeeze, reduce the thickness. So, when it reduces the thickness, the ring expands. So, when the ring expands, it has to maintain the geometry. So, we use an ideal roller and a main roller. So, you can see here how the ring is made. High strength rings which are used for aerospace application, they are made by ring rolling. It is a deformation process in which the thick walled ring of a smaller diameter is rolled to a thin walled ring of a larger diameter. Ring rolling is a very interesting process. It has lot of applications. In boilers, the rings are also made out of a ring rolling process. There is also ring piercing process. See, if you wanted to use rollers, pierce it and form a tube. This is the starting material. You have a mandrel which pierces it. This piercing will try to bring in tensile load, and this will try to have a compressive on the top. So, here there will be a crack which is formed and you will try to have a hollow shape. So, the rolling piercing is a specialized hot working process for making seamless thick wall tubes. Seamless tubes are, these are tubes where there is no seam. If you take an ordinary sheet and roll it, you will have something like this, right. So, and then finally, what you do is you try to weld it. So, these are all seamed tubes. So, seamless tubes are done by rolling process. So, two roller which are there in opposite direction, hence it is grouped into the rolling process. The process is based on principle that which, so when you try to squeeze it, there is a compression. So, at the center there will be tensile. So, you push a mandrel, so it tries to form a pipe. You can also have other application, corrugation also can be done. But rolling also is not straightforward, it produces lot of defects. So, you can, in the appearance it will be like this. So, it is called, this one is called as center bulging. So, if the cold or hot rolled mill have too many crowns, the mill will roll out and it will have a center buckle. This is a waviness which is created because of residual stresses which are there. The fiber at the edge are longer than the center one. So, it tries to create the waviness. Okay. So, these are some of the defects which come out of rolling process. So, in the appearance you will have this, these are bed leveling and these are edge cracking. Because there are not sufficient material, there will be tensile and compressive forces. So, you will get this edge cracking, right. So, the length of the fiber are increased from one edge to the other. So, it is almost like a taper also, you see it is a taper, bed leveling, and then edge cracking is this. So, these are the defects, these are the causes and these are the corrections which are made. You can also have zipper cracks, these are cracks which are seen all along the line, and you can also have something like a alligator crack. So, the contact is there and once it rolls and it comes out, it forms like a crack like this. So, these are all improper stress strain applying or the process parameters, the velocity, roll pressure, everything. So, if we start optimizing this, we can try to reduce it. So, the camber on the can prevents the defects. So, these are center splitting, this is alligator crack and this is center splitting which can happen. To recapitulate friends, in this lecture we saw what is forming, then classifications and mechanism, process in forming, what is the rolling operation and rolling mills, rolling analysis we saw, outcome analysis, operations of rolling and rolling defects. Okay. So, this will try to give you a very good idea about the rolling process in metal forming. I am going to give you a simple job which is to be done. You please try to take dough and then you try to take a roller. Okay. Roller. So, if I put the side view of a roller, it will be something like this. So, this is a flat plate, this is the dough. Now, you take the roller, this is a roller. Now, the roller you will try to vary the speeds of rolling faster, right. So, vary the roll speeds by 3 levels, 1, whatever it is in your level you can do. Next is you will try to make some grooves on it, make grooves on it, and then you try to roll at 1, 2, 3 speeds. After every pass, try to measure the thickness by using your smart mobile phone side area. You can try to take the thickness and also try to take a photo in the plan view or from the top. You will see several different shapes getting formed. So, these shapes are nothing but defects, and once you do this exercise, you will have a perfect understanding what are the process parameters, how does it affect the raw material, and then so. And you should also try to have one last example, that when we try to do this dough, first you give a powder coating on the flat plate, and next you do something without a powder coating. Powder coating is given, and one with powder coating and then without. You see the surface, what it happens. When you do this exercise at home, you will completely understand and appreciate the rolling process. These are the references which we have used. Thank you so much.